unknown. What is that? What are they? They are F1 and F2. So two unknown, okay? Two unknown parameters. Two unknown, I cannot say parameters. Two unknowns. Now, how many equilibrium equations? Okay, how many equilibrium equations? You have to count the equilibrium equation, not equilibrium equation, to see whether this is the same as the unknown. Unknown is the forces. So unknown is F1 and F2 and force equilibrium. Now, what kind of force equilibrium do we have? Well, let's say this is X. And this is Y. And this rotation is a Z. Now, force equilibrium is let's say, x directional force. Okay, x directional force. And this and minus W equals 0. Why? Because this is a plus X. We have a W minus F1, F2 is a plus. So this is certainly one equation in x directional force equilibrium. Now, second very important equilibrium is the moment equilibrium. Moment equilibrium, this bar certainly is moved, and then it stay there, right? It does not rotate. I mean, motion. We don't have a motion. We don't have a motion. You just sit and rotate and stay there. In other words, forces are 0, and rotation, we have to have moment equals 0. How do we consider the moment? Now, moment is a little different from a force, but conceptually same. But moment is the amount whether this is a rotate or not, right? But it's a stay there. It does not rotate, which means that this point does not rotate, and that point does not rotate. Any point, they don't rotate at all, right? In other words, when we consider moment equilibrium, we can pick this point and see the moment equals 0. Well, we can pick this point as we consider moment equals 0. So you can choose any point, actually. If this point does not move, then will this point move, rotate? No. So any point can be picked and consider moment equilibrium. That means other point would not rotate neither. So in this case, we pick this point and see the moment, and this F1 times A is causing this moment, and B times F2 is causing that moment. So there will be a plus and minus. They have to be 0. Okay. Or you can pick this point and this W and this way and F this way will give us the same result. So moment equilibrium, you can pick any point you like to consider. So now how many equations? We have 2 equations. One is the X force and moment, and we have 2 unknown. So can we solve F1 and F2? Yes. What is F1? F1 will be W1 plus B over A. F1 will this, that, right. Now F2 will be A times B, A times B, B times A. So W1 plus A over B. So now look at this result, very important result. Look at F1 and F2. It's all function of what? Force and length. You remember when you have a task 1, your homework, there's some F1 or F2, 3, 4. You remember F2 is a function of what? K1, 2, 3, right? K1, 2, 3. But do they have any material property, K1 and K2? No material property. which means that this reaction force is hanged by the spring. And let's say we change the material property or different spring, but always the force is the same. So this is the characteristics of statically determinate problem. As the word says, statically determinate. Equilibrium-wise, it can determine, which means that we don't need to have any material properties. So that is a very important point. Another simple case of statically determinate is that another statically determinate is the case like we have a very typical clamped beam subject to an end load. Now, let's consider this one. Why is it statically determinate? Well, say we have a length L and we have a, say it's made of steel. Now, let's take a look at the free body diagram and P, and unknown, which we don't know, is the how much forces. There should be some reaction force and there should be some moment reaction, right? So those are two unknown. Again, equilibrium wise, this is let's call X and Y, and X, force X is that R minus P equals 0. So R equal P, that's it. Even no length, no material property. Material property means we don't have to consider whether it's a steel or rubber or a aluminum, right? And moment 0, we consider moment equilibrium. So moment, we pick this point, we can pick this any point, we pick this one, and this is a M0, so plus, and this one cause minus, so minus PL. So this is 0. So moment 0 is what? P times L. I know you know you can solve, but we need to like to digest the results. As again, all the reaction force, which means that you hold this beam and push. How much you hold it, nothing to do. This is a pen or aluminum or plastic, doesn't matter. All the reaction force is the same as that. And all the moment it rotate will be just a P times what? This M length. In other words, you have an airplane. All the load are from this aerodynamic load, right? And all the load is a self-weight or passenger weight. So it's a force-wise equilibrium. So if we look at this wing and can be simplified like that, and all the load. Well, this is a little different from this, but conceptually very same. So we can say this one is the P. Again, all the reaction force is determined by this length and this force. Okay? So our wing also complicated structures. All should be result will be very complicated. No. We are mechanics. We need to understand how the equilibrium goes. Okay? So very important result. Now, but let's consider similar but different case. The same beam made of steel, but we hold it at the both ends, here and there. And then we applied some point P. Now, let's count, or let's draw the free body diagram. One is here and there. So this is R1 and R2 and M1 and M2, right? That are certainly reaction force. How many reaction force? We have a 4 reaction force. How many equilibrium equation do we have? Same. I mean, X, Y, and moment, right? So equilibrium equation will be only 2. 2 equilibrium and 4 unknowns. So this is what? Statically indeterminate. What does it mean physically? Well, if it's made of steel, made of aluminum, all the reaction force now is different. This is made of rubber, and same force, same length, but the reaction force will be now changing depending on the material properties. Okay, so that is the very important observation. Difference statically determinate indeterminate. I mean, mathematically, equilibrium is the equation. They don't have any material property. So statically determinate, of course, is only determined by the external force. So anyhow, this is a statically determinate and indeterminate, and not because by the dimensions, but because of a number of unknown equations. That would make a big difference. Okay. Now, next one. Any questions on statically determinate and indeterminate? Okay. Very quiet means question mark. Okay. Now let's move to the next chapter. What I'm trying to do is cover whole lecture notes. Okay. Now I like to spend about 50 minutes and cover a very important subject about uniaxial deformation. Chapter 4, we're gonna cover chapter 4 and chapter 6, okay? And next week we will cover chapter 5. So chapter 4 and chapter 6, okay. In the very beginning, we briefly reviewed the what kind of structure we cover in this class. Is that basically 3 structures. One is a bar, second shaft, and third beam. And geometrical wise, they are pretty much the same, similar, and meaning that cross section is like this and very small compared to length and cross section. I already mentioned this one last week. But beam and shaft and beam, what makes different? Difference is the what kind of a load each member carries. So at the end or in the middle, there can be 3 forces and 3 moments, right? 3 forces, 1, 2, 3, and moment-wise, 1, 2, 3, right? So 3 force and 3 moment, there are 6 components of a force are carried by each section. Now this force-wise Fx, X component of force, I just say Fx, and Y and Z, I use the V. Why? Fx is carried by the bar, then it's called bar, and shaft is also moment, but x directional moment, axial moment is called torque, and is carried by shaft. So among these, from those 6, x and tx each carried by bar and shaft, but the rest of vy, vz, moment y, moment z are all carried by beam. These 4 forces are causing curvature or bending of these structures. Okay, and as you can see here, this Vx is causing some moment z, Vy causing moment y. So they are kind of related, which makes beam little complicated than other structures. So beam is so important. Another 2 reasons. Well, equation is very complicated. Second, in most of the structures, a material fail under this beam bending load. So anyhow, each member we consider equilibrium, stress, and so on. Now, what we try to cover will be this one. Okay, this is what we're gonna cover, but not just for the 1D, but in general 3D case as well. Okay, so let's go to the case of beam, the bar. Okay, bar. I know you already know the Young's modulus, right? We already know the Young's modulus. But what's the physical meaning of the Young's modulus? Well, we certainly need to clarify the meaning, Young's modulus. Now, this is the A bar, okay? A bar, and we apply the force P here. And then certainly there will be in negative direction, there will be a reaction, and P. And now, and in any section inside, let's cut this one. I mean, fictitious cut, not the real physical cut. And this one will have a P, and how much the reaction force we will have is a P. And on the left-hand side, this is the external force, this is the internal. You can see that this internal is also P. So from this free body diagram, we can see that any sections, we can see that there is a force P. Okay, this is just one consideration. Now, importantly, we have a bar with the length L and cross section A, and this is a P, and let's say there is a delta there. Okay. Now, let's consider the case when we double the force P. We doubled, increased twice. What will happen to this delta? Well, you can simply say is that deformation will be doubled. Do you agree? Yes. So P or delta, we can say it's proportional to a P, right? That's for sure. Now, another point we can consider is the increase the length. Increase length, let's say from to double length, just increased. And there will be a twice of delta compared to this. And same P and same A. So delta is proportional to L. right? But I don't need to further explain this. Now, let's say let's increase the A, double increase. Now, what will happen to this delta? Right? Delta will reverse, decrease, right? Decrease by half. So delta will be inversely proportional to A. So if we combine all those three observations, we can say delta is a proportional PL over A, right? Now, okay, remember this equation. I will rewrite here. Delta is proportional to PL over A. Now, I'd like to change this P on the L on the left-hand side here, and A goes to here. So P equal, so P is proportional to what? A delta over L, right? Okay, so this is one. Now, to make it equal, what is the missing part is the material property. Now, the amount of, the proportional constant will now depends on whether it is a steel or aluminum or rubber. So there, we need to introduce a Young's modulus which will control or represent the material. So E, A, delta, L. So here comes the Young's modulus. In other words, this one, you can say EA over L and delta, which is very similar to force and K, and this is a spring constant. So in a bar, the spring constant will be EA over L. So what is the E? Again, it's called Young's modulus. Now, what is it? Do you, anybody knows the value of the Young's modulus of the steel? Steel, what's the Young's modulus? Huh? Yes, 200 gigapascal. That is the Young's modulus of a steel. Now, all of you have to remember these numbers. 200 gigapascal. What is a giga? Giga is a 10 to the 9, right? What is a pascal? Newton per A. Newton per meter squares. So 200, 10 to the 9, and Newton per square meter. This is a pascal. This is a Young's modulus. So actually, you can easily see that here. You can divide by A. So P over A. Now E will delta over L, right? So this, what is this? What is that? And now this E is now defined this term and that term. What is P over A? P over A. Let's draw the cross sections like that. We apply certain force P. What does it mean? We apply force P. Well, over the section, P means that we apply certain uniform pressures like that, and all the pressure, I will call pressure as a sigma as the P over A. Force per unit area is called sigma. Okay? Now this is sigma, this is a sigma or pressure in this case. Okay? pressure P over A will be, what is the delta over L? Deformation per unit length. So I will call this one as a strain, a Y strain. Well, we will come to that one again. But this stress equal E times strain. So stress and strain, Young's modulus is a material property which relate to a stress and strain. So now strain, okay, what is a stress is kind of clear, but what is a strain? I will consider this case. Let's say we have a 1 meter and it extended 1 centimeters. So this material would extend. Imagine how much it has a strain in there. Something changed. Now there is another one, same one, 1 meter and 1 centimeters. Okay, this is exactly same amount of strain. Now we attach these two members together. What does it mean? We attached it together, so we have this and we have that. So one member. Now, how much deformation we have? This is totally 2 meters and totally 2 centimeters, right? So this member, whole member, will have a certain strain, but this strain and that strain is all same, right? So strain-wise, 2 centimeter by 2 meter or 1 centimeter by 1 meter is all same. So this is the amount we have to consider inside the materials. Delta is not so important, okay? Delta, we cannot judge how much strain, what is going on in the material, we cannot judge. We cannot make clear decisions. Because simply it's a longer, small amount of force will have some very big displacement, right? So displacement per length is the amount to represent strain level inside of the material, and stress is the amount of force per unit area. That's the force we apply. That is the deformation we have in the material, and this is a material properties. Okay, so I briefly come to a definition of a stress and strain. And what is this? Young's modulus. This is easy. I know. Yes, it is easy, but conceptually, we will extend this one-dimensional concept to two-dimensional and three-dimensional. Okay? So at this level, you have to clarify, really crystal clear. You need to visualize. Now, I'd like to spend a little time to what is the 200 gigapascal? You see, 200 gigapascal. How big is it? How big is it? So we will do some experiment. Okay, experiment means that let's consider 1 meter long steel bar and 1 centimeter by 1 centimeter cross sections. This is a steel bar. 1 centimeter is about this much cross section, and 1 length, 1 meter, and we will put here, and then I will hold it. Or some of you will hang and just attach to this one, and then we want to see how much delta. This is made of steel, and in other words, Young's modulus is 200 gigapascal. Problem is clear? So this is in my body or your body. What's your weight?
80kg.
Huh?
80kg.
Okay, he's 80 kilogram. Okay, and steel bar 1 meter long and cross section 1 centimeter by 1 centimeter. Now this steel bar will extend a little bit, right? How much? Can you guess how much? Don't calculate, just guess as an engineer.
0.1mm.
Okay. Delta, his estimation or guess is 0.1 millimeters. How about you? What will be your guess?
0.10분의 0.01.
0.01 millimeters. Actually, 0.1 millimeters is very small. You cannot even see that, right? It's a thickness of a paper is about 0.1 or 0.05. So it's order of a thickness of your paper. That's the amount. 1 meter, and you just hold it, how much it extends? Let's calculate it. Sigma equal E epsilon. We do know that, right? And sigma, what is a sigma? P over A, and this one, E, and L over delta. Delta is the one we want to calculate, right? And what is the P here? 80 kilogram. Kilogram in Earth, in gravity field, what you need to multiply? 9.8 meter per square, and this is 8 kilogram, right? So this is 80 G in gravity. Divide by A, what is A? Point by, this is, 1 centimeter by 1 centimeter means that 0.01 meter by 0.01 meter. I want to change all in meter and Newton, okay? And equal, now what is the E? 200 gigapascal. Giga is 10 to the 9. And what is the L? L is 1 meters, so 1 meter and delta. So delta, let's calculate it. 9.8, well, let's call it 10, okay? 80, well, let's call it 100 kilogram. I don't mean you are that heavy, but let's consider 101. So, and then let's calculate 10, 1, 2, 3, and 1, 2, 3, 1, 2, 1, 2, 4, 1, 2, 3. So 10 to the 5, right? Oh, sorry. 10 to the 7, right? And divide by 200 and 10 to the 9 meters. So this one, say this one is a 10 to the 11, and okay, 10 to the 7, this is a 2, and then this one, so 1 over 20 millimeters, right? 10 to the 3 is a meter, and so this is a millimeter. So which is 0.05 millimeters. So it was a good guess. So when you have this much length, this much strength, this much weight, the extension will be just 0.05 millimeters. Very, very small. In other words, steel is that much very stiff. I really want you to remember this number, okay? 200 gigapascal. We as an engineer, you should know how to visualize, how to make judge. You don't have to remember any other numbers just for the comparison. Aluminum, well, you can say E is about 70 or 860 or 50 gigapascal. Aluminum is about 1/3 of the steel, okay? E, plastic, 1 giga up to 3 gigapascal. This is very small. And you can see that 200 is kind of reference, and you can easily understand how soft or how stiff. Carbon fiber, very stiff, will be 300 gigapascal, which is even stiffer than steel. Okay? So anyhow, I really want you to recommend you to remember this 200 gigapascal. Okay. Now, next one. Now, well, this is how we measure and how this, and very important, another material property is Poisson's ratio. What is a Poisson's ratio? Poisson's ratio is that you need to pay attention. I will quickly jump to 3D from this. So please pay attention. So this one, let's say P apply or sigma, P over A, we have a sigma. Certainly we have a delta X over Lx. What is this? Epsilon, right? And sigma and epsilon, we have Young's modulus. But there is another deformation, is shrink, which is as important as this deformation. How much? Well, this is a 30% of this. That's it. 30% of this amount. Not the deformation. 30% of epsilon, I will call this is X. 30%. 30% of epsilon X is epsilon Y. Epsilon Y is this much strain. And this is a shrink, so there will be a minus here. And so this one is called Poisson's ratio. So Poisson's ratio is simply, as shown here, Poisson's ratio is minus epsilon Y divided by epsilon X in this case. But pay attention to this epsilon X. Amount of delta Y, amount of delta X, a little different story. Why? Because this epsilon Y is this is the length and this is the delta Y. So delta, this is very small. Why? Delta Y is small. But in terms of strain, that is the 30%. So I will rewrite here. And delta Ly and delta Y is minus 30% of delta X and delta Lx and delta X. Okay? Okay, that's the deformation of definition of a strain and Poisson's ratio. But there is not only this, but there will be another Poisson's ratio. And this one is also shrink. So when you extend, this will shrink and that will shrink. Very, very, very important. Okay? So deformation wise, we have sigma x, okay, causing epsilon x, epsilon y, and epsilon z. This one, 30% of this, and this one, 30% of this. This is the same. Okay? So you need to remember this. Now, another important point is shear strain. What is a shear strain? You know, so far we just consider this, right? Sigma x. This is a 1D version of a stress. Now I'd like to expand 2D version, means that here we can have a sigma x, exactly same sigma y. Now, there is a one term appear in 2D case. What is that? In this surface, we can apply this force, but we can also apply that force. Okay, this one. So that I will just use it here. That we can apply. Okay. But let me ask, is it equilibrium? No. Certainly not, right? Let's say this is x and this is y. Is it equilibrium? No. To make this structure or component equilibrium, what else do you need? You need to have this one, right? Right? So Fy will be 0. But is it equilibrium?
No.
Not really. Why? Because it's a rotate, right? So you want to reverse this one. You need this force to counteract this rotation. But is it rotate? I mean, is it equilibrium? No. Why? Fx is not equilibrium. So you need this. So now your Fx is 0, Fy is 0, and moment equals 0. This is the shear stress we have to have. Always this, that. That's the only way we can apply shear stress. Okay? So in 2D case, we want to have a tangent force, but that cannot apply alone. We have to have this, and we have to have that, we have to have that. So this is a 2D version of a stress. Okay? But how about the material deformation? Well, deformation-wise, this guy, I will use this one for the shear case. How we deform? Deformation. Well, there's no x force, no y force, but somehow it's like that. Yes, so it will deform like that. So only deformation is the angle change. Here we have angle change, angle change, angle change, angle change. Shear stress is causing angle change. See, this guy is what is causing length. Length has changed. Length has changed. But this 90 degree, all same, right? Only this length. But this shear, the changing, length does not change, but only length, only angle. Okay? So, that's a 2D version. Now, Now, let's extend to the 3D. 3D, stress. Okay. 3D, we have a brick body. Now 3D, as considered it's a 1D, we have a this, and this, and this. They are all tension, 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 right? Now shear, we have this and that, and it's hidden here and there, right? But there is another shear in 3D, which is this and that, and backside. And another one is this and that and another side. So simply, this is a 3D version of a stresses. So this one, we have a one component. How many components? This one? 1, 2, 3, right? One component, sigma xx, and 3 components, and 3D is a six components. 3 normal and 3 shear. This, okay? 3 shear, 3 normal. That is the 6 component. These are 3D version of the stress. Now, how about the deformation? Well, deformation, very similar, conceptually very similar. This one, we have an extension, and we have an extension, and we have a angle change. So it's difficult to draw, but we have a 3 component of strength. And it's the same thing, 3D strain, we have a this deformation, and that angle change. So in 3D, I will jump to now here. 3D, now this is the stress component. Remember, we start with this, right? We start this P, and this is a sigma x. That was a 1D version. We always have this. This is a 1D version, and this one is the 2D version, and now this is a 3D version. As you can see here, each surface we have a sigma xx, one normal, y one normal, and z we have another normal. And this one we have a shear, right? As here, right? 2D version, and this is a 1D version. And here, now we have another set. This another set. I mean, the back side we have it, right? Back side we have another one is this and that. So each surface, look at that, one normal and 2 shear. Because a area we always have a shear 2 component, right? This and that. Normal is only 1 component. And here the same thing, 1 and 2 and 3. And this same thing, 1 and 2 and 3, right? So each surface we have a 1 shear and 1 normal and 2 shear. So 3, totally 9, but these are same, that is same, and this is the same, so totally 6 components. That is the shear 3D version. And component-wise, I will like to, you have a nice picture here, better you can better understand. And now, very important, okay, I need to go through this one. And here, for example, this one, okay. We already studied this, but sigma x we apply, and this one now trying to relate stress and strain. Stress and strain. How many strain components? 6. How many components stress? 6. So 6 and 6, there is some relation. Just imagine sigma equal E epsilon. Okay? This is just a 1D version. Now we are trying to have a 3D version. To get the 3D version, we simply change this one as just inverse, but very important inverse. Epsilon equals sigma over E. So this is the I mean, same one, but this is a strain given stress. Now here, let's consider epsilon x is a sigma x is a 1 over E because this is an extension, right? Now there's another term by sigma y. Sigma y, what will happen to here? Shrink. How much? Because this one, 30% of this, so minus 1 over E sigma y and Poisson's ratio. Right? And how about this sigma z? Yes, sigma z also causing epsilon x because this will shrink. So minus E sigma z is the amount of this extension. There will be a Poisson's ratio. Okay? This is the final relation I'd like to draw for 3D case. And same story goes to epsilon y and epsilon z and so on. And please remember sigma x, sigma y, and sigma z. So all put them together into one big matrix. Remember, see epsilon x is the 1 over E sigma x, right? And epsilon x is sigma y. Now 1 over, now you understand, there's a minus, Poisson's ratio, y divided by E, okay? And sigma z also shrink epsilon x, and there is minus Poisson's ratio and Young's modulus. Exactly same story goes to epsilon y. Let's take a look at epsilon y caused by sigma y, right? That's the definition of Young's modulus. And now sigma x will shrink. In here, when you apply, I'm trying to, this one will cause this. And now this guy will change this much, and this is that is another one, right? So this one, and now epsilon z, exactly the same, and epsilon z caused by what? Sigma z, 1 over E, and Poisson's ratio minus by sigma x and sigma y. Okay, so these three and 3 is a 3D version of strain, material property, and sigma, which is exactly same as strain, 1 over E, and stress. That's a 1D version, right? Now we can extend it to a 3D version. It is called superposition. You know what is a superposition? You add them. Effect due to sigma x, effect to sigma y, and so on. It's just a linearly superposed. But conceptually, it's very important, very similar to 1D version. Now, there's another important, well, everything is important. Another one is, what is this? What is this? You remember this term? What is this term? This term is representing only shear, 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 right? So 1 component, 2 component, and 3 component, right? So those are 3 components. But look at that. This one, just pay attention to this 1 component, this one guy. And this one guy is this. And this is a sigma xy. And this guy only change the deformations of this angle change. So sigma xy doesn't do anything except epsilon yz, which is the angle change. It does not change the others, so only this term. So in other words, let's say we have a brick, okay, and we apply the shear. When we apply this shear, only angle change. If you look at this one, it's just like that, just like that. It doesn't change. So figure-wise, we do have a figure. It's something like that. When you apply the shear, only like this and like that, and this and that. So this angle change is the gamma or tau. You know the gamma and tau? But anyhow, we call gamma in sigma xy, we call gamma as a epsilon xy. In more precise, consistent terms, mathematics, sigma xy rather than tau, epsilon xy rather than gamma. But anyhow, this does not cause any deformation, something like that one, okay? Only that strain terms. And that's why we have this and that and that. See, why these are zero? See, when we apply this guy, does not extend. That's why we zero. What is these terms? Well, when we apply this and that angle does not change. So each term has some meaning. How many terms do we have here? 6 by 6, 36 term, right? But each term has a meaning. What is this guy? Tension and extension. What is this guy? When we apply this and how much it shrink. What is this guy? Each term has it. What is this zero term? When we apply the shear, extraction, no difference, right? So that's why it's zero. So each term has its own meaning. Very important observation is that they are all same. It's same. They are, we call mathematically, this matrix is symmetric. Matrix is a symmetric, linear algebra. I'm sure you already studied a lot about this symmetric. Symmetric matrix has a very important physical meaning. All stiffness matrix have to be symmetric. But there's a big another story, but it's important to observe this symmetric matrix. And this one, conceptually, as I mentioned, just this is the 1D version, and this whole 46 term is a 3D version. And 2D version, what will be the 2D version? 2D version will be this guy and that guy, right? Sigma xx. You remember these terms and this and that and that and that and this, right? So xx and yy and sigma xz. So this guy, that, and this, that. So this term and that term and that and that. How many? 3 by 3. This is a 2D version. And so this matrix is, since it's a 3D, we can shrink to 2D, shrink to 1D. What is a 1D? This, and that, right? That is a 1D version. So again, this is the material property. We start from a very strict, right? F and F equal Kx. Now extend it to a concept, sigma equal E epsilon. And then we reverse epsilon equals sigma divided by E, and 2D version and 3D version. Why 3D version is so important? All the body, everybody, and all 3D materials can be any airplane or even bio, anybody, any materials. When we have a certain forces, certain geometry, and there is something going on inside. So we pick very small material here, and we look at this, how much stress we have, how much stress on each surface. That is a 3D version. 3, 3, 3, so 9, symmetric, 6 component. And this will deform. This is a stress, and this will strain. How much it deform? Deformation and stress is different, right? So how much is strain? Well, this will shrink, and this one, and say this, because of that is causing this much extension and deformation, so on. And this relation is in 2D. This is epsilon and sigma, and this is the Young's modulus, and this is the extension to a 3D. Okay, so now we need to start from a 1D spring, 1D material, and 2D. Now we have a 3D. So every material we have, even body or any structures, there is always a 3D stress is going on inside, and 3D deformations. And this is the concept we apply to whole flow chart over here. This one extends to a 3D. Now, how many stress components do we have? 6 components. 3 normal, 3 shear. So 6 components. How many strain components? 6. 3 normal and 3 angle change. Now stiffness, how many? 6 by 6, 36. Okay, you remember all the terms? 36, 1 over E minus E, and this and that, right? So this is the what? And strain, and this is a stress. Now this is a stress, and simply we started from F, K, X, right? That was the concept, start from the spring. Now this one, we can inverse. We can come to a sigma. We can inverse this one. And this is like F, K, and X. So all material has this stiffness, which act like a spring, and how much deform, and how much force. So force and deformation exist inside the material, but this force, 6 component stress, they cannot just stay they like. No. They cannot exist arbitrarily. Why? This one has to be controlled by the equilibrium. Remember this guy, and adjustment, there is another guy, another guy. All they have to force equilibrium. So all the stress is controlled by equilibrium, which is like a spring and spring and spring, all force equilibrium, right? So all the stresses have to be controlled by equilibrium. Now, deformation. What is the deformation? Well, deformation-wise, the spring is like that. They have to deform together, right? Very similar concept. This guy, when it deform, they have to certain meet condition. Why? Because deformation, we have only UX, UI, UZ, but this is a 6 component. So 6 component, there have to be some restriction. We cannot have arbitrary deformation. So this is the older story. So we have to meet this equilibrium, we have to meet this stiffness material property, and we have to meet deformation condition. That's how material will deform under external forces. Every material, everything, we have to, the material, we have to follow this physical meaning. Okay? Just another one last point I'd like to mention. I just rephrase my point. Say, say, where are we? Okay, you tell me, now you as a mechanical engineer, you want to be a designer, right? You want to design your own product and you want to do, come to a certain idea, or you want to develop a automotive or bike. Okay, let's try the bike. Look, no bike. But it's okay. Somehow we don't have a bike, but this is the, any component is okay. Do you see this old color? Yes, you see this color, right? This represents only one component of 6 components of stress. If you show, we have a, can see sigma, this is a sigma xx, we can see the sigma yy, and ZZ and so on. We can see these all 6 components. You can also see this one. I cannot show you right now, but you can see epsilon XX, epsilon YY, epsilon ZZ, and so on and so on. So we can see the sigma X, 6 components, sigma XX inside the body or surface and strain. How do they, what control this distribution? 3 rules. One is the equilibrium and stress-strain material property relation and strain displacement. So that is the one, and we cannot just solve by hand. Well, spring is easy, we can solve, but in this, this is some link system or some I don't know why we cannot have a bike. Huh? Okay, this is the a bike. We have this is the rear wheel, right? And this can be a fork and another one, and so I'm sure we could have some, this is the, the wheel here, right? And there we have a fork and front wheel and handle here. And there's a seat. Is that correct? Okay, there's a seat. And you are riding, sitting here and then, so what you see here, all the color, well, say you have a big impact, front impact, or you're too heavy. You can see how much stress. This is the, you remember how many components of stress? 6 components, just one of them is shown here, color-wise. And you have a 6 component of strain, right? And you can show just one component. You cannot see all the 6 components together, right? But I just want to help you to visualize how this 6 component and 6 strain component exist in any body. So say this red color here, right? What does it mean? It's very critical, very high value. Very high value. That's why once we calculate the stress, if this stress guide too high compared to strength, that bike will break at that point. So that's how you do as a designer. The brake should not fail, right? And also, bike has to be very light. So you want to reduce the weight as much as you can, but without any failure. So we have to consider force and material and this and externally, but you control all the thickness and get the best bike. Okay, get the best bike and lightest one. I mean, this is just one small example. You can apply to any component. Well, I can really show you another one. Oops, I missed out one. I say CAE is a computer-aided engineering, right? All the you know the wind turbine blade, and you can see all the colors and different members, and it shows all the stresses. And so this is how we design. The figure-wise, there's not much figure in here. I hate this. I don't like. I like the Google. And as you can see here, this is one blade of three wind turbine blade. You know, the wind turbine blade, and you can see how much is stress, and you can see how much inside. And this is the design by mechanical engineer using computer-aided design CAD file. And then once you apply all the load here, you know, all load from wind, and you get all the forces and the stresses and the strain component, as I explained. Okay, so this is all you do after you graduate. You get a job, and that's what you do. So as a mechanical designer of structures. Okay, so any questions? What we cover? So again, I'd like to give you a global view. Today, we cover the definition of material property and brief introduction of stress, strain, and material properties, and chapter 4 and chapter 6. Now, next week, Wednesday, we're gonna have online course. So how you do an online course? Don't worry, I will send you an email and invite you attend a online course. All you need to just relax and sit down. You can sit or you can lay down, do whatever you like. You can watch. Okay? And there is a program called Zoom. Okay? There is a program called Zoom. And when I invite you, this one will automatically invite and install the software and things, and you have to be there on time, okay, on Wednesday. So all the presence will be checked automatically. Any questions? Okay. So see, and Thursday we're gonna have in class. So see you Thursday, but on Wednesday, see you online. Okay, thank you. I will assign the homework, okay, through emails. Okay, I will assign the homework. Don't worry, we have a homework.
교수님 질문이 있는데요. 혹시 이게 그 줌이라는 것이 혹시 핸드폰으로 되고
Yeah, you can watch your handphone. Yeah, cell phone is okay.
시간에 뭐라는 게 그 정해진 시간 내에.
그렇지. 그 시간에는 방송돼.
근데 그 시간 말고 다른 시간은 볼 수 없는 거예요?
그 시간에 봐야죠.
그 몇 시부터 몇 시까지?
수업 시간.